Okay, so I told you about this lab last week where we were going to do a lab and we were going to look at how efficient and how effective the conversion of potential energy into kinetic energy was. And I've been doing this lab pretty much the same way for 8 or 10 years. And I had an absolute brainchild. And I decided this is a better way to do it. So we're going to try this. We're going to be the first ones, okay? But we're going to try it a different way because I think it's going to be a lot easier. I tried it myself quickly at lunch, and it's way more consistent than the old way. The old way is that the way I was telling you about, where we take the rubber band and we put the Hall's carriage, little cart in, and we shoot the cart out. Well, the problem with that is they almost never go straight. And they always end up running into stuff, okay, or they flip over, and acquiring the data takes forever. And then I thought to myself, you're stupid. Why not convert gravitational potential energy into kinetic energy instead? Because something going down a ramp is much more likely to travel in a straight line when it leaves the ramp than something shot by an elastic band. Plus, we can use way better carts. Instead of using the little Hall's carriages with tiny little plastic wheels, we can use the dynamics carts, which have excellent wheels. Okay, so we're changing it up a little bit. Okay, the problem is going to remain the same. The problem is still that we're going to try and find out how much of our available potential energy, this time it'll be gravitational, will be converted, okay, to kinetic energy in a mechanical energy conversion. And that's what we're doing. Okay, we're going to lift the car to the top of the ramp. When we do that, what are we doing? We're giving it potential energy, we're doing work. Okay? When the cart rolls down the ramp, it's going to convert that potential energy into kinetic energy. So our challenge here is, it'll be easy for us to measure and thus calculate the potential energy because we'll just measure how high the ramp is. And we'll know the mass of the cart because I'll put it on a scale and calculate it for everybody. Okay? The problem here is going to be, and this is the same problem with the old lab, how do we calculate the kinetic energy? Because we need to know then how fast the cart is going when it gets to the bottom of the ramp. And there's no way for us to measure that. So what we're going to do instead is we're going to measure how far the cart travels after it leaves the ramp. Because after it leaves the ramp, what's going to start to happen to it? It's going to slow down. Why? Because of friction, right? Friction is essentially taking energy from the cart because the cart is doing work against friction. Everybody follow me there? Okay, so if I can calculate, I'll be able to measure the distance it travels, will that be the distance over which friction did work on the cart? Yes. Okay, now, on your formula sheet, we have this formula here. Remember I told you, we never use that formula? Guess what? We're going to use it. Not on the test. It's not going to be on the test tomorrow. You're not going to have to use this on the test. But we're going to use it for today because it's going to do a job for us. It's going to allow us to calculate the force of friction. All we have to do is calculate the acceleration of the cart, which we'll be able to do if we not only measure how far it travels, but also time how long it takes for it to stop. All right? So we're going to use a couple of formulas today that won't be on your test, okay? But that we've actually kind of used a little bit throughout the unit here. Okay? They'll allow us to get the data we need, and I think it's going to be a lot more consistent than using the rubber band. We would be doing the same calculations with the rubber band, but we wouldn't get nearly as consistent a data as we're going to get doing it this way. Okay? Everybody follow me so far? Okay. So the design, okay, our variables here. What are we manipulating in this experiment? Right, the potential energy. Okay? By setting up this ramp and then placing the car at the top of it, we determine how much energy, mechanical energy, it has to begin the experiment. Right? Does everyone follow me there? That's kind of a big giveaway, as I pretty much gave it all to you there. All right? What's our responding variable? What are we using that to calculate? How far it goes we're using to calculate its. We're also using that to calculate this. Energy, what kind? Kinetic, right? Because that's what we're comparing here, right? We're comparing the potential energy at the beginning to the kinetic energy at the end. Okay, we want to see how much kinetic energy it has at the bottom of the ramp. And is that responding to how much potential we give it at the beginning? Right? I mean, it would seem to, right? Okay. Our controlled variables. We're only going to do this thing a couple of times, okay? But we're not going to change the ramp any. We're just going to set it on some books and we're just going to run the cart down it, okay? But we'll do a couple of trials for consistency's sake. What are some things we're probably not changing throughout the lab then? The height of the ramp, the length of the ramp, the car you're using, okay? Don't change cars halfway through, okay? What's that? So, you got to have 3 controlled variables. I think we've gone over a few there, okay? You got to explain to me why we're not changing those throughout the lab. In our hypothesis, okay, the hypothesis needs to work something like this. In the if part, you need to tell me what the theoretical relationship between the initial energy and the final energy is. Theoretical. That's what we've been working on over the past week, by the way. Okay, what the theoretical relationship between initial and final energy is. Okay, the and part describes the experiment, same as always. The then part needs to tell me what the experiment is really going to show. Okay, so our materials are already listed on here, and I did take the mass. I remember, that's right. I put that on there. The mass of these black carts, and these are the ones you have to use, okay? Because we designed these ramps. Mr. Dickey and I designed and fabricated these ramps, okay, ourselves, so that they would fit these black carts. Okay, the black carts fit in them very, very nicely. Okay, they work really good. But if you try and use these ones, they don't work. Okay. Well, actually, they do work, but they're going to move around a lot, so you don't want to use those. They have special carts. We have special tracks for those. Okay, we're using these carts here. Okay, you just place them in the ramps. Now, these carts are all 0.470 kilograms, all of them. Okay, because they're all exactly the same. All right, so they're all 0.470 kilograms. Okay, when we're going through this, there's some things that we need to measure along the way. Okay, mass of the cart, already did that for you, so you know what it is. Initial height of the ramp. All right, so when we're measuring that, we want to measure from the floor, okay, to right here at the top of the ramp. And then we need to make sure we put the back wheel of the cart right there. Everyone follow me on that? Now, that means, though, when we measure how far the cart travels after leaving the ramp, we measure to what part of the cart? The very back, for consistency's sake. Okay, so those are some measurements we're going to need. For the potential energy, we need the initial height of the ramp and the mass of the cart. For the kinetic energy, mass of the cart, which is going to be the same, the distance traveled by the cart after it leaves the ramp, okay, and the time of travel. It says here also final velocity of the cart, but we know that that's going to be 0 because it's going to stop. All right, so we got to time it and we got to measure how far it goes. When do we start timing? No. Once it's off the ramp. Okay? Don't start the timer until it's left the ramp. All right? Otherwise, you're timing part of its accelerating phase rather than its decelerating phase. We're only worried about while it's slowing down. So once the back wheels are off the cart, start the timer. Stop the timer when the cart stops. Okay? Everybody with me on that? All right. And then there'll be some values that we'll have to calculate. That's part of the analysis. Okay, you can see in here, analysis questions, calculate the work done in putting the cart on the top of the ramp, which essentially means calculate your potential energy. Okay, calculate the acceleration of the cart using your average distance and time, and that is explained to you here in part 2A. This is the formula we're going to use to do that. Okay, that'll get us the acceleration of the cart. Okay, and then we're going to calculate the kinetic energy of the cart, which we'll do using this formula. mad. Mass times acceleration times distance, because mass times acceleration gives me force of friction. So is this force of friction times distance? Okay? And is that what the kinetic energy is being used to do work on? Yes, it is. Okay? So this will help us get EK without having to use this, because we don't know what that number is, and we have no way to measure it. Right? So we're going to bypass it, and we're going to do it a different way, this way. Okay? For number 4, outline how you determine the potential and kinetic energies. We've talked about that. If you listen to the podcast, I've told you essentially in here where are you getting your potential energy from, where are you getting your kinetic energy from. Okay? This is a big part of how we're calculating the kinetic energy, is that we're using this instead, not this formula, but we're using that there's a force being worked against over a distance. Okay? And then for number 5, did the potential energy of the system equal the system's kinetic energy? Why or why not? You're going to include in there something you're going to learn tomorrow. Okay? In there you're going to include the efficiency, and that's a percentage, and I'm going to show you how to calculate that tomorrow. All right? It's not due till Friday, so it's not a big deal if you don't get that question done, okay, today. Okay. How high does this ramp need to be? Yeah, no more than that. No more than 15 centimeters. If you make it more than 15 centimeters, the cart will travel too far, and it'll run into the wall. Okay? And that can't be the way that it stops, because we have no way to calculate how much work it does on the wall. Okay? We can only calculate how much work is done against friction when it coasts to a stop. Okay? So no more than 15 centimeters. Okay? A little less than that will probably work too. And each group will just set up in the aisles between the rows. Okay? There should be enough there for everybody, and then no one's carts will run into each other. No, the string is on there because we have a lab that we do in one of the other classes where we tow these things around. Okay? So I think they're actually all off anyway. Some of them still have a string on. Right? And then you'll have your conclusion and evaluation, same as always. Okay? Did your hypothesis work out the way you thought? Basically, in this one, you're going to have to tell me, you know, theoretically the relationship was this, but it did or didn't work out that way, and then maybe why. All right? That'll be part of the conclusion. Evaluations, your sources of error, okay, and ways to correct them. Are there any questions on what we're doing here? Okay? Once again, what things do we need to measure? Okay, so we got to have distance traveled, time, height of the ramp, okay, those are the ones, and the mass, which I already did for you, and it's on there. Okay, those are the things we got to have in order to get the calculations the way we need them. Now, you're going to have a chart that's going to look like this. Okay, this is the data I got when I did it, so it works. It's nice and consistent. Okay, so what you guys will do is you'll fill in your own data. You're going to do 4 trials. Record how far the cart travels each time. Okay, first time for some reason it went really far. I'm not sure why. The rest of them were much more close together. Okay, and your times. Then calculate your acceleration for each trial. Okay, and then you're just going to give me an average of each one in these boxes here. How are you going to get these averages? Add them all up and divide by 4. Okay, that's all you have to do for the averages here. All right. For EP, I think actually in your file this says NA in all of these because it's the same for every single one. You just show me the calculation you did down here. Okay, everyone follow on that? Okay, so show me mass times gravity times whatever height you put your ramp to. Right? And then for this one here, it'll be EK is M times A times D. Do that for each trial because it'll be different for each trial. Okay? And give me an average down below here. Okay? Everybody follow? All right. Grab your equipment. Okay? The rulers are underneath the ramps, so you'll all have to grab ramps before you can grab the rulers. Okay. Now that you've got all of your data, okay, and you've hopefully got this chart pretty much filled in, now it's time to do some calculating. Right? The first thing we've got to calculate is acceleration, and it tells us in the procedure that we want to use this formula to do that. A equals 2D divided by T squared. This D is this. Okay? The distance the cart traveled. The time is this. The time it took for it to come to a stop. All right? Punch those things into this formula and fill in your acceleration here. Then, there's a bunch of you not listening. I'm not going to repeat myself. Okay? We got to calculate EP. We only have to do that once because it's the same. We put the cart on the ramp in the same spot every single time. M times G times H, whatever the height of your ramp was. Okay? Then we got to calculate kinetic energy for every trial. That's going to be mass times the acceleration for that trial times the distance it traveled. Okay? So you're going to have the mass of the cart, 0.470, times whatever acceleration came out to, multiplied by this number, and that will give you EK. Right? Then you can start looking at the analysis questions. All right? Everybody follow me there. Well, actually, the analysis questions are partly filling in this chart. Okay? After that, you got some analysis to do. Okay? Okay, listen up here, guys. I think this is what's confusing people. It's that I put the NA in every column here. Okay, you only need to this number is the same in this whole column here. That's why I only have the bottom one blank. But calculate it down here and then put that number in every box. That way it all looks the same. Then for this, you go mass times acceleration times distance for this row. Okay, mass times acceleration times distance for the second row. Okay, so just so you don't get confused, just take those NAs out, okay, and put in whatever you calculate in the bottom, okay? Remember I showed you that's mass times gravity times height. Just put it in every column here. Here. Okay, so the due date for this is this Friday. Whether you and your family are leaving early for Christmas, which you shouldn't do anyway, but if that applies to you, you should first off see me for an extended absence form. Then secondly, this is due for you. I don't care where in the world you are. Okay? You'd best be here. That's where you're supposed to be. Okay? But if you and your family are leaving early, this lab is still due for you on Friday. If it is not submitted by you on Friday, it is late. Is that clear to everybody? Yes. Okay, no exceptions will be made. Beginning of class, same as always. So what do you guys have? It starts at 11:30 something for you guys. I think I set it for 11:30 on there. If I didn't, I'll change it.